In this talk, I'm going to introduce the theory of relativity. That's the theory that we need when things are moving at an appreciable fraction of the speed of light. When we first encounter relativity, it's a theory of measurement, the way we measure times and the way we measure distances and how those are related to each other in an interesting and unexpected way. One of the most powerful things about the theory of relativity, however, is that it also impinges on the way we think about matter and energy. And the whole thing, as you're probably well aware, was originally devised by a famous physicist called Albert Einstein in the early years of the 20th century. So we're not going to cover the whole theory today. We're going to cover one of its more startling predictions. It's something called the twin paradox. And the reason I'm focusing on that is because it's fairly easy to demonstrate. The mathematics involved isn't too difficult. And the origin of the twin paradox actually is very firmly rooted into what we know about light, the phenomenon of light. And I'm going to start by reviewing for you some facts about light, which I hope you're already familiar with. We're then going to cover something called the Doppler effect, which is what happens to light, what it looks like when the light source, the thing emitting the light, is actually moving, either moving towards you or away from you. And once we've thought about that for a while, I'm going to then set out the what are called the postulates, the basic ideas underlying the theory of relativity. I'm going to show you, or try to persuade you, that they're very firmly rooted in observations and experiments which have been done. And once we've set all that up, then we can go ahead and introduce our twins, who in this lecture are going to be called Alice and Bob, and we're going to review some of their adventures and show you the very remarkable paradox that results when people move very fast. So without further ado, let me lay out for you 4 facts about light. The first fact is one we actually know from a very young age. Light travels in straight lines. And the evidence for this is startlingly easy. It's around us all on a sunny day. It's the existence of shadows. So the fact that light can't go around corners means that if something gets in the way of the light source, like the sun, then a shadow is cast which is relatively darker. So shadows are evidence for light traveling in straight lines, and in fact that's true so far as we know, as long as we're thinking about distance scales which are much greater than, say, typical wavelength of light, and we'll come on to that in a minute. The second fact that we're going to need about light is that it travels at a finite speed. And the reason this isn't obvious is because that speed is absolutely enormous. It's 3 times 10 to the 8 meters per second, or 300,000 kilometers per second. And we need to stress that that's way faster than any speed normally encountered or experienced by a person running or driving a car or flying a jet plane or even traveling in a rocket. So that's one reason why relativity isn't very familiar to us. It's simply because most of the time we don't explore anything like those speeds. How do we know that light travels at a finite speed? Well, one reason is that we can look up into the sky and we can look at objects which in effect we can use as clocks. So one example would be if we look at the planet Jupiter. It's got 4 moons orbiting around it in a very regular and well understood way. However, Jupiter isn't always the same distance from the Earth, depending on where Jupiter is in its orbit around the Sun and where the Earth is in its orbit around the Sun. Sometimes it's further away. And in fact, when people observe the behavior of the moons, you can see that sometimes the clock is running a little bit more slowly than you might expect. So that when, say, one satellite gets to its furthest distance from Jupiter, it happens a little bit later than you might expect. And the most natural and simplest explanation for this is that the light from Jupiter and from its satellites is taking time to get from there to here. And that's because it can only travel as fast as 3 times 10 to the 8 meters per second. And of course, this is a commonplace observation now. We know from space missions when we send probes to the outer parts of the solar system. In fact, we know that the signals that we send to control the probes and that the signals that the probe sends back to us, maybe photographs or scientific observations, that can take, well, several hours if it's from way out in the furthest reaches of the solar system. So although light's speed is very, very fast compared to our common experience, actually the consequences of it being finite are well understood. The third fact about light is that it's a wave motion. And that means that it consists of waves, and we can characterize those waves by the distance between successive wave crests, and that's called the wavelength. It's usually denoted in physics by a Greek symbol lambda, and that's what I've written on the slide here. And because light is traveling with this enormous speed, those wave crests are passing us. And so we can also characterize the light by something called the frequency, which is the number of wave crests which pass us or which enter our eye, say, in a second. And that number is called the frequency. And in fact, the relation between the two is that the longer the wavelength, the lower the frequency, or the shorter the wavelength, the higher the frequency. And in fact, if you multiply the frequency by the wavelength, it always comes out that the product of those two quantities is equal to the speed of light. So it's interesting to talk about frequency because it's responsible for one of the most obvious qualities which light has, and that is the color of the light you see. So it's a fact that light of different colors has different frequencies. One thing we're going to use in this talk is that red light has a lower frequency than blue light, and that's what is written there on the slide. So I hope that actually most of these things you already knew, but these are the things we're going to use to develop our ideas and ultimately will lead to the theory of relativity. So one way in which these ideas relate to each other and kind of lead to something interesting is when the things which are emitting the light are in motion. Because when light is emitted from a moving source, that can actually lead to its frequency with which the light is observed being shifted. There's a name for this, it's called the Doppler Effect. And one place that we can actually observe the Doppler effect is if in the night sky many stars we observe are actually part of what are called binary systems. That means they're actually two stars, and they may be orbiting around each other, much like the planets orbit around the sun. And that means that at any given time, one of the stars may be moving towards us, and the other star will be moving away from us. Now, when the star is moving towards us, the light which it emits looks a little bit bluer than we might have expected. In other words, its frequency is larger than the frequency we might have expected to see. How do we know what color light to expect? Well, we know that because stars emit light in with characteristic frequencies related to the chemical composition of their atmospheres, and we can examine that by taking what's called a spectrum of the light. So actually we can measure this shift in frequency by comparing the spectrum of the starlight with the spectrum of a sample of gas or whatever chemical it is taken in a laboratory. So the Doppler effect says that the light from an object moving towards us is bluer than we expect. That's sometimes called a blue shift. By contrast, the light coming from the star which is moving away from us looks redder than we expect, and that is because its frequency is less than the reference frequency. Now, the interesting thing is about a binary system is that the stars are constantly orbiting around each other, so that the star which for now is moving towards us, a certain time later will be moving away from us. And at the same time, the star which is now moving away from us will be moving towards us. So if you observe the spectra of these stars, you'll see a kind of a dance. The spectrum will be split into two, with one component slightly bluer than we expect and one component slightly redder than we expect. And those will move apart and then move towards each other and merge and then move apart again in a regular pattern, which we can relate to the orbit of the stars around each other in the sky. And what that means is that the light we observe from binary systems exhibits regular color variations. And that's a very interesting observation, and it actually helps us to work out the properties of the stars in question. So it's a very useful tool in astronomy and astrophysics. Okay, so now let's focus for a little while on Albert Einstein, the physicist who first developed the theory of relativity. Most of us know about Albert Einstein. We know that he's an old man with fuzzy grey hair and a very impressive moustache. He looks extremely wise, and he's become a bit of an icon. You'll find his photograph everywhere on the internet, on t-shirts, on tea towels, and he's got a lot of very wise sayings about the ways of the universe, which many physics enthusiasts like to quote. So this is perhaps our mental image of Albert Einstein, and it's actually very startling that when he developed the theory that we're talking about today, he looked a lot more like this. He was a young man. He was in fact 26. And it's, I find, a rather disturbing fact. He's much closer in age to you than he is to me. So it just goes. This just goes to show that our image of what physics, science, and what the people who do it is often doesn't really match the reality. Very often, very startling things are done by quite young people. Okay, let's launch into the theory of special relativity, as originally set out in a very famous paper Albert Einstein wrote right at the beginning of the 20th century, 1905. It's based on what are called two postulates. The first postulate is that the velocity of light in a vacuum, that means when it's not going through a medium like air or glass, the velocity of light is constant. It doesn't depend on how fast the thing emitting the light, the source, is going. It doesn't depend on how fast the thing receiving the light or observing the light is going. Everyone who measures the speed of light will always get the same answer, that number we called c, 3 times 10 to the 8 meters per second. This is actually quite a surprising thing, and it appears to defy common sense, where we think of, if we think of light like a stream of bullets or missiles, you would think that if a star, say, that is moving towards you and emits bullets or missiles, they'll be going a little bit quicker because they'll have the speed of the star added on. Well, if that were true, it would have observable consequences. If we think about the binary star system again, if the blue shifted light was traveling faster than the red shifted light, it would get from the star to the Earth sooner. And therefore, this regular pattern of the two spectra, the point of maximum blue shift and the point of maximum red shift, they wouldn't be in sync. They'd be all over the place, and it would be much harder to disentangle what was going on. And there's no evidence from our observations of binary star systems that that's going on. It's much, the observations that have been made are all consistent with the fact that the red shifted light and the blue shifted light have got from the stars to the Earth in the same time. They've been moving in the same speed, And the only difference between the light from the stars is in the shift of their frequency. So that's the first postulate of special relativity. The second postulate, the laws of physics are the same in all inertial frames of reference. It's impossible to perform an experiment to detect absolute motion. What does that mean? First of all, I'd better say what an inertial frame of reference is. That means that you're in a frame of reference where you, the person at the center of things, are either at rest or you're moving in a straight line with uniform velocity. It means that you're not accelerating. And it's important to say at this point that the theory of relativity that we're outlining today is all to do with inertial frames of reference. We're not talking today about anything which is accelerating. That's a different and equally important, if not more important, story, but it's beyond the scope of what we're talking about today. And that's why sometimes the theory we're talking about today is called special relativity, because it applies to inertial frames. How might an absolute motion be defined? Well, one way in which it would be defined is if there were a medium which carried the light waves. It's not unreasonable, because the other signal, which is a wave, which we know about and are familiar with, is sound. Sound is a sequence of oscillations of alternating pressure, high pressure and low pressure, in air. And sound is therefore carried by a physical medium. We can feel air, we can measure it, we can compress it, we can measure its density. So when people first start to understand light in terms of a waveform, it was very natural to think that there would similarly be a medium which carried the light waves. And if something's natural to think about, it's natural to give it a name. The name that it was given is called the ether. Well, we know that sound is carried by a physical medium, and we can actually measure its properties. One way in which we know about the air is if we go outside on a windy day. If the air is in motion around us, we feel it. We feel it in our faces. We find it difficult to cycle against. In fact, we could even detect the wind and the speed and direction of the wind by doing careful experiments with sound, because the speed of the sound moving against the wind is slightly different from the speed of sound going downwind. So a characteristic of a medium is that it alters the speed of the light waves. Could we therefore detect an ether which carries light waves by measuring the effects of a wind? We know that the Earth is in orbit going around the Sun and moving actually rather fast, perhaps 30 kilometers per second, something like that. So surely, if the Earth is moving through the ether, then there'll be an ether wind, and we should be able to measure it by carefully measuring the speed of light along the direction of motion of the Earth and at right angles to the direction of the Earth. This was a very natural way to think at the turn of the 20th century, and in fact, two scientists called Michelson and Morley performed they did better than think. They performed an experiment to see if this ether wind could be detected, because they worked out the size of its effect, and they built apparatus which was capable, in principle, of detecting the difference between the way light traveled along downwind and across the wind. And one of the remarkable things about that experiment is that it failed to detect any wind effect at all. And so the Michelson-Morley experiment is direct experimental verification for the second postulate. It's actually, they were trying to do something which was impossible, which was to detect an absolute frame of reference with which we can define absolute motion. And what this says is that, as it says in the postulate, the laws of physics are therefore the same whenever they're measured by anybody who's in an inertial frame of reference. Okay, so let's keep these postulates in mind. I'll try to point out to you when they come in, and we're going now to do an argument to show how they might lead to some interesting effects. In order to do that, we're going to consider a diagram of people in motion. I'm going to label the people as A and B because that's the easiest way to write labels with simple letters. But it doesn't hurt if you actually extend it and think of A as being an observer called Alice and B as an observer called Bob. So in order to talk about their motion, we need to talk about where they are, their distance from where they started, and also when they are, so the time that's elapsed. So therefore, it's very natural to portray their motion on a two-dimensional graph where the distance across the horizontal axis measures distance and the vertical axis measures time. So what's drawn here, this red arrow, is Alice's trajectory. What you can see is it's going straight up the graph. That means that her distance from the origin is the same at all values of the time. What that means in real words is that she's standing still. She's at rest. Her distance is not changing with time. And for a particle or a body or an observer at rest, the trajectory looks like a straight line going straight up the page. In contrast to that, this is Bob's trajectory. So at early times, at time 0, at the bottom of the diagram, Alice and Bob are at the same point, and their trajectories therefore cross. But then Bob's trajectory is a straight line moving at an angle. And as time increases, the distance between Bob and Alice is getting bigger and bigger. And it's getting bigger in a uniform way. If you think about a particular point on Bob's trajectory and you measure the distance as the x coordinate and the time as the y coordinate, then you can see that the slope of the line, the time t divided by x, is just 1 over Bob's velocity, v, because velocity is distance divided by time. So what this means is that a straight line at an angle to the vertical represents a moving object. If the line is straight, that means that the velocity is constant. It doesn't change in time. And that's what we expect of an observer who stays within an inertial frame. So the special theory of relativity is all about straight lines in this kind of space-time diagram. Okay. So we're in a situation where Alice and Bob were together at the beginning, and now Bob is moving away with constant speed to the right. Alice would like to do an experiment to measure how fast Bob is going. How can she do that? One way is that Alice can send a signal to Bob, and Bob can, when he receives the signal, can send another signal back to Alice. That signal I've represented as a black dotted line, and that's the most effective signal we can think of sending is a light beam. So one way of visualizing this is to think that Alice is holding a torch and she shines it at Bob and presses the on switch, and a beam of light flies between Alice and Bob. Now, we know from what we learned earlier that the speed of light is finite. So therefore, the trajectory of the light beam is going to be a straight line at an angle. If you look, it's at a bigger angle to the vertical than Bob's trajectory because the speed of light is very big compared to Bob's speed, or it's certainly larger. So therefore, just from the geometry of this diagram, we can see that the signal going from Alice to Bob will eventually intersect Bob, but at a slightly later time because the light needs time to catch up with Bob. Similarly, when Bob gets the signal, he can take out his torch and shine it back towards his torch back towards Alice. And that beam will go at the same angle but in the opposite direction. And it will take some time to get back to Alice. So therefore there's a measurable delay between Alice sending out her light signal and receiving the return signal from Bob. She might also choose to repeat the experiment a little bit later on. It looks very similar, but all of the distances involved and the times involved are stretched slightly, because by now Bob's further away, so the light takes longer to get to him. Well, let's try to put some numbers on this. Let's suppose that Alice sends the signal to Bob after a time t after he initially left. What time does Bob get that signal? Well, that's what we want to work out. For now, we're going to call it k times t, where k is a number we're going to try to work out. But on general grounds, k is going to be bigger than 1. In other words, Bob's not going to get Alice's signal for a longer time than the times that Alice waited before sending it, simply because Alice's signal has to take time to travel all the way from where she is to where Bob receives it. So therefore, in general, kt will be larger than t. Now, think about this whole procedure from Bob's perspective. Bob is an inertial frame, so in his own frame of reference, he thinks he's standing still, and what he's seeing is Alice flying away from him with the same speed, but in the opposite direction. So if Bob waits kt before sending his signal and then sends it back to Alice, the time that Alice receives it will be a factor k times kt, or k squared times t, since the time when they were together. So that stretching factor, kt and k squared t, is the same in both directions, and that's really just a consequence of the special relativity postulates. First of all, that the speed of light is always the same, regardless of the speed of the observer or the speed of the source. And secondly, that it's really impossible to decide whether it's A at rest and B moving, or B at rest and A moving. They're both equally legitimate points of view. Okay. One way of understanding that the time between the light, that the interval that Bob receives the light is longer, has been stretched. It's actually an instance of the Doppler effect. Another way of saying this, therefore, is that the frequency with which Bob observes Alice's light signal is 1 over k times the frequency with which it was emitted from Alice's torch. That's nothing more than the effect that we talked about when we were discussing the binary stars. So our goal is going to be to calculate this Doppler effect factor k in terms of Bob's speed. I'll show you how this calculation goes. It's going to go a little bit quickly, so I would just listen for now. If you want, it will be of benefit to you perhaps to go through these steps again later with a pencil and paper, and you can always replay the slides to get the expressions correct. If Alice works out the time between sending her signal and receiving the return signal from Bob, it's k squared minus 1 times t. And it's very reasonable for Alice to deduce that the time that her signal got to Bob was exactly halfway through, because she knows that light travels the same going from her to Bob and from Bob to Alice. It's the same speed. So therefore, just by doing a little bit of geometry, she can work out that the distance that Bob was from her when her light beam got to him was basically how far light can travel in half the time of k squared minus 1t. And that gives the expression there, c times k squared minus 1 times t divided by 2. So she knows the distance. In order to work out Bob's speed, she also needs to know the time, and she can do that actually by just subtracting, you're using the fact that it was t to the moment that she emitted her first signal, and then it's the half k squared minus 1 times t for her receiving the return signal. And she can do a little bit of calculation and work out that the time, the moment that Bob received her signal, was a half times k squared plus 1 times t. So now let's do the calculation. Bob's speed is the distance divided by the time. We argued that the distance was c times k squared minus 1 times t divided by 2, and that the time was k squared plus 1 t divided by 2. So if I divide one by the other and tidy it up a bit, I can work out that the Bob's speed in units of the speed of light is given by that expression, k squared minus 1 divided by k squared plus 1. And then it's possible to do a little bit of algebra. Again, you might want to do this in your own time to work out the Doppler shift factor k in terms of Bob's speed v. It's the square root of 1 plus v over c divided by 1 minus v over c. So we've used this rather geometrical approach of the space-time diagram to work out the effect by which light from a moving object, its frequency is changed, the Doppler shift which we discussed earlier in relation to the binary stars. There's a couple of things that I'd like to point out to you in this formula. One is that you can think of v either as b's speed away from a, in other words, if you assume a point of view in which a is at rest, but it's equally valid to think of it as a's speed away from b, in the point of view where b is at rest and a is moving away to the left. The same formula works, and that's really, again, a direct consequence of the special relativity postulates. The other thing to notice with this formula is it's got what's often called in physics a symmetry. If I take v and change it into minus v, if I change its sign, that's the same way as saying that instead of the velocity being b moving away from a, that would be the description of b moving towards a. And if I change v to minus v, you stare at that formula, you should be able to convince yourself that it has the same effect as changing k to 1 over k. And that tells you that the same formula can describe both a redshift, where b is moving away from a and k is greater than 1, and it can also describe the case of a blue shift, where b is moving towards a and k is less than 1. And that's nice. It's nice when we have a formula which can do which can serve for two slightly different cases, the red shift and the blue shift. Well, we've done most of the maths now. I hope you didn't think it was too difficult. I'd now like to go back and discuss another little adventure that Bob and Alice could have. And this time Bob is going to stay at home, at rest, so therefore Bob's trajectory is a straight line going straight up the page. Alice goes on a journey, so she's with Bob at the beginning and then she flies away to the right, but at some point she stops. She turns around and travels back in the opposite direction at the same speed. And therefore, the trajectory in the second half of the motion is a straight line at an pointing not to the right but to the left, but it's at the same angle to the vertical. And therefore, at some point in the future, A and B, Alice and Bob, are together again. At the point where she reverses direction, at the furthest extent of travel, Alice chooses to send a light signal to Bob. It could be a simple flash of her torch. It could be something more involved, like, I'm on my way back, put the kettle on. And we can now try to use the same sort of arguments that we looked at earlier to try to work out how the time intervals go. This time, from Alice's perspective, the time that she flies away, the first leg of her journey, I'm going to call t. When she turns back, she's moving at the same speed and she has to cover the same distance but in the opposite direction. So the second leg of her journey is also going to take t. However, because Alice and Bob are flying apart from each other, we know that Bob is going to measure the time of that initial signal, telling him to put the kettle on, not t, but rather an extra factor k times t after their initial, after the start of the journey. That's a manifestation of redshift. K is larger than 1. On the way back, Alice thinks it takes t, and she is sending lots and lots of messages to Bob. And they're all flying at the same speed. And you might be able to tell from this diagram that actually, although Alice is sending the messages at fairly regular intervals, they're actually rather crowding up. And B is getting Alice's return signals fairly rapidly. And in fact, it's because now that Alice is traveling towards Bob, in effect, all her signals are being blue shifted. So therefore, when Alice takes a time t to get back, Bob measures that time as k 1 over k times t. Eventually, Alice gets back to Bob, and they're in the same place at the same time. They can compare their clocks. They can just get them out of their pockets and put them next to each other, and they can compare the duration of the journey. And here's where the amazing thing happens. From Alice's perspective, she took a time t to fly out and she took a time t to fly back, so that the total time which elapsed between the two meetings is just 2 times t. For Bob's perspective, we have to add up kt, the time he measures until Alice gets as far out as she does, and then 1 over k times t, which is the time she takes to get back. Remember, we have a formula for k in terms of Alice's flight speed v. It's the Doppler shift factor. There's the formula. It's quite complicated. So now we can substitute in that expression for k into the formula for the time that b measures. I won't go through the math. It's not too difficult. And here's the answer. Bob's measurement of the time to the meetings is 2t divided by the square root of 1 minus v squared over c squared. Now v over c is always less than 1. So 1 minus v squared over c squared square rooted is a number which is less than 1. So therefore 2t is being divided by a number which is less than 1, and therefore it's going to be greater than 2t. And here's the amazing outcome. The time that Bob measures between their first meeting and their second meeting is greater than the time that Alice measures. They can put their clocks together. They might have synchronized them when Alice set off, but they'll be giving different readings when they get back. And that is the effect that's known as the twin paradox. That different observers, different voyagers who've had different experiences, not only have they gone different distances between first meeting and second meeting, but they've also experienced different time durations. And that's something which we're completely not used to in a world where we don't really travel very fast compared to the speed of light. But if we're talking about space journeys, that effect can actually be considerable. So let's think about a prospective journey where Alice wants to travel to a nearby bright star. The star she's chosen is called Sirius. There's a photograph of Sirius. And it's 9 light years away. That means that a beam of light leaving the Earth would take about 9 years to get to Sirius. Alice has the latest rocket ship. It's capable of traveling at 4/5 of the speed of light, or 0.8 times c. So she sets off from the perspective of B, who chooses to stay at Earth and sit at mission control. How long is Alice's trip going to take? Well, she's got to go 9 light years to get to Sirius. She's got to go another 9 light years to get back. And she's traveling at 8/10 of the speed of light. So the little calculation is laid out for you there. It'll be 22.5 years between Alice leaving and Alice returning. That's quite a long time, quite a significant commitment for Alice's mission in terms of, a fraction of her potential lifetime. But what about Alice? How long does she think she takes? Well, she has to correct that factor by the factor which we just calculated. And on Alice's clock, she thinks the trip takes 22.5 years multiplied by the square root of 1 minus 0.8 all squared. And if you put that into a calculator, you'll find it's significantly less, 13.5 years. This is why it's called the twin paradox, because Alice and Bob could be twins. But when they return after Alice's mission to Sirius, Bob has aged by 9 years compared to Alice. This effect that time can somehow be stretched out or compressed for different observers moving at different speeds, it sounds like science fiction. After all, we still don't really, space travel to nearby stars still isn't really a reality for us, and there are enormous technical challenges to getting rocket ships traveling at 8/10 the speed of light. But time dilation does have consequences in our world. I'll mention one. It's very famous. There are unstable subatomic particles called muons. Muons are produced constantly in the upper layers of our atmosphere by collisions with very high energetic particles like protons coming from deep space. They're called cosmic rays. So muons are produced in our upper atmosphere, and many of them can be detected by detectors or observatories lower down at the ground. And actually that's quite a puzzle, because when we do experiments on muons in a laboratory when they're at rest, the muon's unstable. It actually tends to decay after only 2 microseconds. And the reason this all works is because the muons, when they travel from the upper atmosphere to ground, are actually traveling at 0.9997 times the speed of light, almost at the speed of light. And their effective lifetime in the Earth's frame of reference is therefore dilated. It's not 2 microseconds, it's 80 microseconds. And that gives the muons plenty of opportunity to reach the ground and to be detected as a muon at sea level before they decay. So time dilation has directly verifiable consequences, and it's real, as amazing as it sounds. Final thing I'd like to cover is, why do we call this a paradox? Well, if you're sitting with Alice on her rocket ship and you look at Bob, it looks to you like Bob is moving away from you at high speed, and then at some point he stops and then returns to you equally fast. So from that perspective, if you're on Alice's ship, aren't you the person who's been at rest, and isn't Bob the person who's had the interesting trip? Haven't you therefore had the same experiences but vice versa, the opposite way around, and shouldn't it be Alice who's aged more than Bob? Well, you might think that way, but it's not quite correct, because the experiences of Alice and Bob in this second experiment are not equivalent. The way we phrased it throughout the entire story, Bob remained in an inertial frame. He remained at rest in mission control on Earth. However, Alice, when she got to Sirius, at the very furthest extent of her trip, she had to reverse direction. In practice, that's a big deal. She would have had to have turned on the motors in her rocket ship in the opposite direction, which is going to decelerate, bring herself momentarily to rest, and then to accelerate back in the opposite direction towards Earth so that she could get back. So for that whole period when that was happening, she was accelerating, and the motors on her rocket ship were working extremely hard. So for a brief period, therefore, Alice was not in an inertial frame. She wasn't an inertial observer. And that means that Alice's experiences are not the same as Bob. And that is how we resolve this apparent paradox. There is no paradox because Bob is always an inertial observer, but Alice is not. Well, that covers, I think, one of the more startling consequences of the theory of special relativity, and I hope you didn't find the mathematics too daunting. As we saw, really, a lot of it could be done by just drawing large, clear diagrams and by also thinking clearly. And I hope you've found that enjoyable.